All right, so last week we finished up talking about reaction coordinate diagrams for multi-step reactions. And in this example, we had A converting to B and then B converting to C. And we said when A converts to B, it goes through that transition state that I labeled with that red double dagger. That has its own unique activation energy. And then when B goes to C, it goes through a different transition state. And again, it has its own unique activation energy as well. Generally, when we're looking at rates for chemical reaction, we're looking at the rate that has the largest activation energy, right? So in this case, EA1 is a lot bigger than EA2. That means that it's our rate limiting step, and ultimately it's the thing determining the rate for the reaction. It's important to remember too that you can't isolate your transition states. It's the state in which a bond's being made or broken. However, we can isolate intermediates like B, but that gets a little trickier depending on how energetically unstable it is. So let's talk a little bit about that intermediate too and some of these transition states. And there's a postulate that helps explain some of this. It's called the Hammond Postulate. It makes a lot of sense, but let's write it out. Its postulate states that a transition state, and I'll call this TS for transition state, will more closely resemble the starting material, product, or intermediate that is closest in energy. All right, so I'll give you guys a reaction, and I want you guys to help me out with this. The first reaction we're going to look at has a starting material where there's an iodine coming off of it. And during the progress of this reaction, the iodine is actually going to fall off. So it's going to take both electrons from that covalent bond. What will your product or products be? So another way of thinking about this is there are two blue electrons in that covalent bond. Both of them are hopping over to iodine. You'll have iodide, right? That's the easy one. And then what's left over? It would have to be a carbocation, right? So in this case, it's a cation where that central carbon is now missing electrons, so it has a positive charge. Make sense? We're going to go over arrow pushing in a little bit, but I wanted to give you guys a preview.
Does that make it become trigonoplanar?
That's a great question. So if we look at this compound over here, the central carbon is sp3. What about over here? It's sp2. So you're correct. It would be trigonoplanar. We're going from a tetrahedral compound to trigonoplanar because we're changing the hybridization. Okay, so now what we want to do is draw our reaction coordinate diagram. And this is a simple reaction, right? We've got starting materials over here, so I'm just going to label it starting materials really anywhere. We've got G on this scale, and we've got reaction progress down here. Do you think the products will be higher or lower in energy than our starting material? Higher. Why?
Two charges.
Yeah, because it's charged, right? Specifically, that carbon doesn't like having that positive charge. So I'm going to put products at a higher energy level. And we know it's got to have some activation energy. And what I mean by that is it's not a straight line going from starting materials to products, right? We've got to go over some energetic hump. Okay, so starting material, we said, is going to be this compound right here. And we know our products are going to be iodide over here. So I'll draw that in really quick. And then our carbocation. Both of them are in that product well. What do you think the transition state is going to look like?
More like the products.
Well, let's try to draw it, right? What do you think's occurring when we're at the tip top of that hump? The bond is halfway broken, right? So it's halfway on, halfway off at that point. So the way I like to draw that is do a dash bond, and then we'll have iodide here. I'll bracket the whole thing and then put a double dagger on the outside to indicate that it's a transition state. Then let's zoom in. Over here, this carbon isn't a full positive, instead it's a partial positive. And this iodine isn't a full negative, it's a partial negative. So can you guys see how we're slowly ripping off that iodine? Okay, so now according to that Hammond postulate, do you think this transition state at the top is going to be closer in energy, closer in terms of its structure to the product or the starting material? The product. That's really all the Hammond postulate is saying, is it looks more similar to the product than the starting material because it's closer in energy. It seems kind of like a silly postulate, but it's a really important thing when you're trying to figure out how mechanisms occur. Does that make sense? So let's make a note. More closely resembles the product. All right. So now we need to go back and talk a bit about reaction arrow pushing. So I showed you guys in this reaction, we moved the 2 electrons in that covalent bond over to iodide. This is a unique type of arrow pushing, but there's a bunch of other types too. So let's talk about this. Let's go back and review arrow pushing for acid-base reactions. So in acid-base reactions, we had some acid, HA, and we had our base B. And our base, we said it's really important to show the lone pairs attacking the proton, so the arrow is going to the proton. And then what am I missing? The breaking of the bond with the proton, right? So if you remember, we said double-headed arrows mean 2 electrons are moving, so those 2 electrons shown in blue are going to hop over to A. Now A will have a negative charge, and the proton will now be covalently bound to B with the 2 electrons that used to be lone pairs, and B will now have a positive charge. A good thing to remember is that this is a Lewis base. It's donating electrons, that B. Another way of describing this is that it is a nucleophile. And a good way of describing a nucleophile is it wants a partial positive or a full positive charge, right? So in this case, if we think about HA, A usually is pulling electron density away from that proton. So this proton over here is delta positive, and A is delta negative, which is why it's happy taking those electrons. So can you see how that base wants that partial positive on the proton and wants to pluck it off? That means that it's a nucleophile. On the other end, we've got what's called an electrophile. And this is something that wants electrons, right? Electrophile makes a lot more sense than nucleophile in my opinion. So your electrophile is anything that has a partial positive on it or a full positive. Yep?
Is that supposed to be an equilibrium arrow or one arrow?
You can show it either way. It depends. If it's a strong acid or strong base, that means it's essentially a one-way reaction, but if they're closely matched, then you could show it with equilibrium arrows. Good question. All right, getting back to the arrow pushing thing, though, it's important to note that arrows always show the movement of electrons, not movement of atoms. So it shows electron movement. So let's take a look at one example. One example is when you have a double-headed arrow. That's the same thing as showing the movement of 2 electrons. So for example, in our acid-base reaction, the lone pair was 2 electrons, so the arrow coming from it is going to be double-headed. You do have other examples where you have a single-headed arrow, and this refers to movement of one electron. And it's important to remember that this is going to be your electron source. Whoop. At the start of the arrow. And then you're showing where those electrons are traveling to. Does that make sense? We're not showing movement of protons, we're only showing movement of electrons with the arrows. So another easy way to remember this is that your nucleophile is always going to be your electron source. And typically you're going to have a double-headed arrow from your nucleophile over to your electrophile. And this is going to be your electron destination. All right, so let's try to break these apart. So characteristics of nucleophiles and electrophiles. All right, so I'm going to put nucleophiles on the left-hand side. And I'm going to put electrophiles over here. All right, so how do we define nucleophiles again? Are they electron rich or electron poor? So if we go back up and we look at our nucleophile up here, it was pretty electron rich. It had extra lone pairs to donate, right? If you've got lone pairs that you're willing to donate, that means you're rich in lone pairs, right? You can donate them and be happy. All right, so nucleophiles, a common way of thinking about them is that they are electron rich. Electrophiles, on the other hand, are going to be electron poor. They want the electrons from your nucleophile. So let's draw one, and I want you guys to help me determine whether or not it's going to be a nucleophile or an electrophile. Let's ignore the magnesium. The magnesium is just a countercation. Is this going to be a good nucleophile or a good electrophile? Nucleophile. Why? Yeah, because the carbon not only has a lone pair, but it's got a formal negative charge, right? So this is going to be a really good example of a nucleophile due to this, what did I do? Let's try that again. It's going to be a really good nucleophile due to that negative charge on the carbon. So this is a very electron-rich molecule. So this will be a very, very strong nucleophile. All right, let's try another one. So this one is going to look similar, but again, we want to classify it as a nucleophile or electrophile. And again, let's focus on the carbon. As organic chemists, we're primarily interested in the carbon. Is this going to be electron rich or electron poor as a carbon? Electron poor, right? Why? What about bromine? Yeah, electronegativity. Bromine's going to pull electron density away from that carbon. That means that that carbon is now electron poor. All right, let's try another one. Let's think about water. Is the oxygen going to be a nucleophile or electrophile? Nucleophile, right? Because in this case, it's actually pulling electron density away from those hydrogens, so it's got an abundance of electron density on that oxygen. So this would be a really good nucleophile. Oh, I did it again. Try it again. Okay, so this is electron rich. Let's try another one. Let's think about the cation that we had. So this one in the center right here, is it going to be an electrophile or a nucleophile? Electrophile. It wants electrons because it has a positive charge. So this would be an example of a compound that is really electron poor. All right, let's do a couple more. We're going to do challenging ones this time. Let's think about the pi bond here. Is a pi bond electron rich or electron poor? Does it have an abundance of electrons in it, or does it want more electrons? I would say it's got an abundance of electrons, right? So much so that it had to adopt a new hybridization to accommodate them. So over here we'd say, all right, pi bonds are actually a unique example of a nucleophile. Oh, shoot. I keep on doing that. Are a unique example of a nucleophile because they've got extra electron density in between those two sp2 lobes. So I'll say electron rich. All right, last one. Let's think about boron trifluoride. Is that going to be a good nucleophile or electrophile? Electrophile, why? There's actually two arguments you can make. One is electronegativity, right? So fluorines are pulling electron density away from bromine. Okay, that explains half of it. What's the other half? Empty p orbital, exactly. So if we think about this, this boron has an empty p orbital. That means that it's electron poor. Another way of thinking about this is it doesn't have a complete octet. It's more than happy accepting electrons so that it fulfills its octet. Does that make sense? So in general, you can kind of go through the same process to determine whether or not a molecule has a nucleophilic site or an electrophilic site. A nucleophilic site is always electron rich, and an electrophilic site is always electron poor. Occasionally, though, you might run into situations where you have both nucleophilic sites and electrophilic sites within one molecule. So I'll give you guys an example of that. So for this one, find the electrophile, and I abbreviate electrophile E+, and I abbreviate nucleophile as Nu in the following. And predict the product. All right, so what I've got here is a boron. And over here I've got a carbon with a negative charge, and the countercation is lithium. So what do you think the nucleophilic atom is going to be? Carbon with the negative charge. Okay. So let's label that. So this is going to be our nucleophile. All right, where is the electrophile going to be? Where? Where? So the lithium is just going to be a spectator. That's a good guess because it does have a positive charge, but as a spectator ion, it's just kind of hanging out. Boron. Why boron? Because it has an empty p orbital, right? All right, now we've got to choose our arrows. Are we going to show a double-headed arrow or a single-headed arrow? Meaning, is the arrowhead going to have one barb or two barbs? Why two barbs? It's going to transfer both electrons, right? Okay, so I'm going to show this attacking that boron. Now we've got to predict what this product would look like. So it looks like it's going to actually wrap around and attack itself, so it's going to be a ring. How big will that ring be? Well, we can count. So I'll go 1, 2, 3, 4, 5, right? So it's going to be a 5-membered ring. Bromine's going to be in one of the positions. Or sorry, I keep on saying bromine, don't I? There we go. So that's our 5-membered ring. And our boron has 2 methyl groups coming off of it. Is that it? Okay, so lithium we know is still there. It's a spectator ion in this case, so it's going to have a positive charge. Minus charge on boron, right? We still have to remember formal charges, so now we've got boron with a negative charge. Does that make sense? So let's take a look at a bunch of different common arrow-pushing reactions.
Why would that carbon not be positive? It would totally be not positive.
Yeah, so right now it's got 2 extra electrons. So when it donates those 2 extra electrons, it becomes neutral. If it were to be neutral and lose 2 electrons, then it would become positive. So it's important to remember that that carbon still has 2 hydrogens on it and a lone pair. All right, so let's think about it this way. I'll call this carbon 1, 2, 3, 4. And then we said boron would be 5. Carbon 1 in this case has 2 hydrogens coming off of it and a lone pair. Now it still has those same 2 hydrogens, but its formal charge is going to be neutral. Yeah. Okay, so let's look at common arrow pushing. All right, the first one is proton transfer, which is review. So we said if you've got an acid and a base, this time I'll use equilibrium arrows. We can show the base grabbing that proton, breaking that covalent bond between the acid and its proton. Now we've got our conjugate base that has a negative charge, and our conjugate acid that now has a positive charge. So that's review. Let's try another one, though. This is called a nucleophilic attack. So we're not going to be moving protons around. We're just going to have a nucleophile attacking something else. Sounds malicious. All right, so first things first, we need to identify our nucleophile and our electrophile. So who thinks they know what the nucleophile is going to be? Is it going to be the molecule on the left or the molecule on the right?
Molecule on the right.
This gets a little bit tricky. Another way of thinking about it is what's going to be your electrophile, right? Your electrophile is going to be an atom that doesn't have very much electron density. So if we think about this carbon over here, it's having electron density stolen by everything around it. That means that this carbon is going to be electrophilic. You could make an argument, what about the lone pairs on the chlorine and oxygen? Could they be nucleophilic? They're going to have a really hard time reaching around to attack that carbon, though, right? So what could another potential nucleophile be if it's not the chlorines or oxygens on the compound on the right? Yeah, the oxygen on water. Because like we just saw above, it's stealing electron density from those protons, and it's very electron rich. So I'm going to move these red arrows so we can keep track of our arrow pushing. And we want to show the nucleophile attacking the electrophile. Okay, so nucleophile attacks the electrophile. Am I done? What's wrong with that carbon if we form a new covalent bond to it? Texas carbon. What should we do to fix that? Yeah, break the double bond. Similar to what we saw in resonance, right? If you violate the octet rule, you can break a pi bond and then alleviate it. Okay, so now let's draw our product. All right, what am I missing? Negative charge on the oxygen. All right, we kicked electrons up to the oxygen, so it definitely has a negative charge. What else? Yeah, positive charge on the other oxygen because it donated its electrons. So this would be an example of a nucleophilic attack. Okay, let's try another one. This next one is called loss of a leaving group. And we actually saw an example of this already, so we'll go through this one pretty quick. This was one where we had iodine attached to that carbon, and we said that this iodine can actually pop off and form iodide. That means that it's got a negative charge, and then you're left with a carbocation, right? Does that make sense? And again, we want to show that as a two-headed arrow because that iodine is getting 2 new electrons, not just 1 new one. The important thing to remember with the leaving group is it's the thing with the negative charge that's coming off here. It has to be stable on its own. How can we assess whether or not it's stable on its own? It's a little bit weird to think about, but we talked about this with acid-base chemistry, right? Remember the cardio rules? Yeah. If it's really stable according to the cardio rules, that means it's a good leaving group. It can pop off. So again, these trends that we're seeing come back even outside of the context of acid-base chemistry. All right, you guys ready to see the weirdest one of all?
Yeah.
This is called a rearrangement. All right, so with the rearrangement reaction, I'm going to take a different carbocation. This time the positive charge is going to be over on the lower right-hand carbon. And what's going to occur is that positive charge is actually going to move to that central carbon. So what do you think might be happening here?
A hydrogen atom on the middle part.
Yeah, if we think about it, this has an assumed hydrogen atom, where if we look on the one on the right, the positive charge in the center means that that blue hydrogen is no longer there. Where must it be? On the lower right, where the positive charge used to be. Okay, so now we need to explain this with arrow pushing. So in order to show this, what you do is you show the arrow coming from that covalent bond, moving over to that positive charge, meaning both electrons in that covalent bond are actually moving to that next door carbon, and the hydrogen is shifting over one carbon. This is called a 1,2 hydride shift. And this gets into an interesting situation. Why is this occurring? Why would a hydrogen just move around willy-nilly like that? Well, if we look at this compound on the left, that carbon with the positive charge, is it primary, secondary, tertiary? How would we define it? Primary. So this would be a primary carbocation. What about over here on the right? Is that cation primary, secondary, or tertiary? Tertiary. It's attached to 3 other carbons. In general, tertiary carbocations are going to be a lot more stable than primary, so you'll get these random rearrangements to form a more stable carbocation, if at all possible. And I'll show you guys why this happens too. But let's first do another practice one. Okay, let's say I've got a primary charge here. I have a blue proton coming off here, right? Would it make sense for me to move this blue proton to the next door? So let's draw what that would look like. If I move that blue proton, the carbon it was attached to would have a positive charge, and it would now be attached over here.
You know, because you'd be going from secondary carbocation to primary carbocation.
Yeah, so Dylan was saying the starting material on the left is a secondary carbocation. And the one on the right is now primary. Can you guys see that? It's never going to go down in terms of stability, right? So if anything, we want to go from primary to secondary, or even better, secondary to tertiary, but we don't want to get closer to primary. So this reaction just will not occur at all. However, a rearrangement does occur, so let's try to figure out what might be going on. Okay, if we can't move a proton from the right-hand side, what maybe could we move that's on the left-hand side? Yeah, we can move a methyl group. So what we're going to do now is we're going to move this entire methyl group all the way over to that next door carbon. So now this methyl group, you see how it's located right there now? So again, I moved it plus its 2 electrons, which means we must have a charge somewhere. Where must the charge be? Yeah, the one on the left in the center there. And this one actually works out a lot better, right? Because now we're going from a secondary carbocation to a tertiary carbocation. And this is referred to as a 1,2 alkyl shift. Does that make sense? So you can move protons or you can move entire carbon groups over one adjacent atom. Does that make sense? In order to increase the stability of that carbocation. Let's make a couple of notes though, because this does confuse students a lot of times. You can only move a hydrogen or alkyl group to the next door atom. Meaning you can't move it 3 carbons over, for example. It can only occur 1 position over. Yep.
So when you say alkyl group, you mean we could move something even like a propyl?
Yeah, it could be an ethyl group, it could be a propyl, it could be a phenyl group, it could be any carbon-containing group. Yeah. And then the second thing is assume that if rearrangement can occur, that it will occur. If you form a more stable carbocation. Oh, sorry. Does that make sense? Yeah. Up this way?
So like the organ up to the bottom.
The heads of lost.
Oh, sorry. I completely misinterpreted that. What are you talking about? Yep.
So there's still an energy requirement for rearrangement.
Yeah, so there still is an energetic barrier for moving an entire carbon chain over or a proton over, but the reality is it's energetically favorable, so your delta G will be negative in that process.
Okay.
Yep. All right, there's one last type of arrow pushing. And I'm only going to show you one of them. And I'll show you an example of it. Let's say we've got peroxide around. One thing that can happen with peroxide is you can have what's called a homolytic bond cleavage. And in a homolytic bond cleavage, the bond between oxygen and oxygen is being cut. One electron's going to oxygen on the right, and one's going to the oxygen on the left. So let's draw the products that we get out. What's the formal charge going to be for the oxygens? Neutral, right? So they're still neutral. We haven't given them any formal charge, and we need to show movement of one electron by using those barbed arrows, not the double-headed arrows. What do you call a compound that doesn't have paired electrons? Does anybody know? Radicals, right? So radicals are compounds that have unpaired electrons. They tend to be less stable, but you do see them a lot in organic chemistry, and we'll cover those more in second term. But I did want to introduce you to them. What do you think a heterolytic bond cleavage would be? Where both electrons move, right? So an example of a heterolytic bond cleavage would be something like loss of a leaving group, where both electrons between carbon and iodine moved over to the iodide, right? So that'd be heterolytic, meaning they're not going opposite directions. All right, so let's go back and talk about carbocation stability, because we're going to see a lot of this carbocation stuff in the next chapter. I don't know if we'll have time to get to the arrow pushing activity yet, but we'll push that off till tomorrow if we don't have time. All right, so carbocation stability. We already mentioned that tertiary carbocations are more stable than secondary, are more stable than primary, and these are way more stable than methyl carbocations. Right, so increasing stability. In fact, the methyl carbocation you almost never observe in organic chemistry because it's super duper unstable. So now the question is why? Why are tertiary carbocations more stable than secondary and so on? And we need to go back and talk about resonance because it's never going away. So let's recall conjugation / resonance. Right, with that we said if you've got a carbocation, it can be really stable if you move that pi bond over. That allows us to delocalize a positive charge across the left carbon and the far right carbon, right? So this is very stabilizing. Hyperconjugation is related to this, but you don't have full resonance delocalization. So let's take a look at what hyperconjugation is. I'm going to draw out an example molecule. And this carbon, I'm just going to assume has some R groups attached to it. And the carbon has a positive charge. What hyperconjugation says is that this attached alkyl group is stabilizing. Which makes sense because we know tertiary groups have 3 alkyl groups, and that's more stabilizing than if you only have 2, and that's more stabilizing than if you only have 1. So let's explain this using orbital theory. All right, so the carbon on the right-hand side with the 2 R groups attached, what hybridization will it be? So this carbon right here. It'll be sp2, which means that those R groups are going to be in sp2 lobes, but what other lobe do we need to pay attention to? The empty p orbital, right? Okay. Now let's think about this carbon over here on the left-hand side. Is that sp2, sp3, sp? sp3. Okay, so I'm going to draw this over here, and I'm going to show one of the sp3 lobes going up to that. So we know sp3, I'm not going to do all of them just to save time. We know out here we've got this attached hydrogen, right? really all hyperconjugation is saying is that this sp3 lobe can help stabilize that empty p orbital by being slightly aligned with it. So if you think about a pi bond, right? A pi bond is two parallel p orbitals that are sharing, right? In this case, you've got a p orbital and then an sp3 lobe that's slightly cocked out. So it's not in perfect alignment. It can't form a pi bond, but what it does do is slightly stabilize it. It's better than nothing, right? So in this case, it's going to stabilize that carbocation. So it's a stabilizing interaction between sp3 lobe with a neighboring carbocation. My number one pet peeve when I hear about hyperconjugation is I hear people try to say, well, that methyl group's electron donating. Not exactly, right? It's not pushing electron density in. It's more that slight orbital overlap that allows it to be more stable. So it's not electron donating that's causing this. Does that make sense? Okay. Another note, too, is that resonance / conjugation is more stabilizing than hyperconjugation. So, for example, up here, we had this compound where we said, this is really stable. Some students will look at this and they'll say, but it's a primary carbocation. And I will say, yes, but it has resonance, right? Resonance is more stabilizing than hyperconjugation, which means that this is super stable due to resonance. And is not like a normal primary carbocation. Does that make sense? Yep.
At parentheses, this is just a minor thing, but in the parentheses of conjugation, you forgot a name.
Oh, I did? Oh, thank you. All right, I think that's where we're going to leave off today, since I obviously can't spell. What we'll do tomorrow is when we come in, we'll do the quiz. I'm not going to put arrow pushing on the quiz, so don't panic. We'll do the arrow pushing activity tomorrow after the quiz. So make sure you hang on to it, bring it with you tomorrow, and we'll do it after the quiz.
So this stuff won't be on the